All right, today we're going to unlock a concept that's really a cornerstone of efficient software. It's a super simple trick that dramatically speeds up how computers find, well, pretty much anything.
I mean, seriously, what if you could take a search through 1,000 different items and I could guarantee you'd find your answer in just 10 steps? Not 1,000, just 10. It sounds kind of like magic, right? But that's the incredible power of what we're talking about today: binary search.
So, how in the world does it pull this off? Well, it all comes down to one core brilliant idea: the halving principle.
Okay, so here's the formal definition. Binary search is an algorithm that works its magic on a sorted collection of items. And that word, sorted, is absolutely crucial. We'll come back to that. The key here is that it just repeatedly cuts the search area in half. I mean, think about that. With every single guess, you get to throw away 50% of the remaining options. It's this relentless division that makes it so incredibly fast.
And you know what? This whole concept is surprisingly intuitive in the real world. Just imagine you're looking for a book on a perfectly sorted bookshelf. You wouldn't start at book number 1, right? Of course not. You'd jump right to the middle. If your book's title comes later in the alphabet, you instantly know, okay, I only need to look at the right half. If it's earlier, you look at the left. Just like that, with one glance, you've thrown away half the books on the shelf. And you just keep doing that, having your problem over and over until you land on the exact book you need. It's genius. All right, theory is great and all, but let's make this real. We're going to walk through an actual search, step by step, so you can see exactly how this works in practice.
So here's our challenge. We need to find the number 7 inside this small sorted array. The list is 1, 3, 3, 5, 7, and 9. Let's trace the algorithm's path together.
Okay, step 1. First, we define our search space. The low index is 0 at the very beginning, and the high index is 5 at the very end. We calculate the middle index, which turns out to be 2. Now, what's at index 2? It's the number 3. Here's the crucial comparison. Is our target, 7, bigger or smaller than 3? Well, it's bigger. And because of that, we know with 100% certainty that our number cannot be in the left half of the array. We can just throw that entire half away and move our low pointer past the middle.
And see? This is what's so brilliant. Our search space is now way smaller. The low index has moved up to 3, and the high is still at 5. We calculate the new middle, which is index 4. And what's at index 4? It's the number 7. Boom! We've got a match. In just 2 steps, we've found our target. So the algorithm returns the location, index 4. Simple, clean, and, as you can see, incredibly efficient.
Now, that example was pretty quick, right? But the real magic, the really mind-blowing part, happens when we scale this up. So let's talk about the logarithmic speed boost and really get into why this algorithm is legendary for its performance.
So think about it. If we were to do a simple linear search, we'd have to check every single element one by one. In computer science, we call this O of n complexity. Basically, the time it takes grows right alongside the number of items. But binary search is a totally different beast. Its complexity is O of log n, or logarithmic time. And what that really means is that even as the list gets absolutely massive, the number of steps grows, well, incredibly slowly. The difference between the two is just staggering.
Let's really visualize this, because this is where it gets crazy. To find one item in a list of 1,000,000 elements, a linear search, well, it could take up to 1,000,000 steps. Makes sense. Now guess how many steps binary search takes in the worst case? A maximum of about 20. No, that is not a typo. 20 steps versus 1,000,000. This is why binary search is so fundamental to high-performance computing.
So here's a quick breakdown of the complexity. The time it takes, as we've said, is O of log n for the average and worst cases. The best case? That's O of 1. That's if you get super lucky and the very first middle element you check is your target. And the space complexity is also excellent. The version we just walked through, the one that uses a loop, uses constant space, O of 1. If you write it recursively, where the function calls itself, it uses a little more space, O of log n, just to keep track of all those calls on the stack. Okay, so the concept seems simple, right? But listen, the implementation details, they matter a lot. So let's talk about the code and some really common traps that can trip up even the most experienced developers. And hey, don't just take my word for it. The legend himself, Donald Knuth, pointed out that even though the basic idea is pretty straightforward, getting the details just right is surprisingly tricky. And he's right. This algorithm has a long, famous history of subtle bugs popping up, even in professional, production-level libraries.
So, what are these tricky details we're talking about? Well, first and foremost, you absolutely cannot forget that the data must be sorted. If you try this on unsorted data, you're just going to get garbage results. Second, these things called off-by-one errors with your low and high boundaries, they are incredibly common and they can lead to nasty infinite loops or cause you to miss the element entirely. And finally, there's a classic famous bug related to how you calculate that midpoint.
And that brings us to a really crucial piece of advice. You see, the simple, naive way to find the middle is low plus high over 2. But that little formula can actually fail with very large numbers, causing something called an integer overflow. And get this exact bug existed in major programming libraries for years. The safe, robust way to do it is with this formula: low plus high minus low over 2. It's mathematically the same thing, but it completely avoids that overflow risk. Use this one.
Okay, but what happens if your sorted list has duplicates, like a bunch of the same number in a row? A standard binary search might return any one of their positions, and you don't get to choose which. So if you need the very first or the very last one, you'll need to use slight variations of the algorithm. They're often called lower bound and upper bound, and they're specifically designed to find the precise edges of a range of duplicates.
Phew, okay, we've covered a lot of ground here. So let's distill all of this down into a final toolkit of key takeaways, the stuff you really need to remember. Here are the 4 things you absolutely have to burn into your brain. Number 1, the non-negotiable prerequisite is that your data must be sorted, no exceptions. Number 2, its speed is its superpower, that incredible O log n time complexity. Number 3, implementation is tricky. Be super careful with your boundaries and always use that safe midpoint formula. And number 4, this is not just some academic exercise. It's a fundamental pattern that comes up constantly in coding interviews and in real-world software.
So we've seen how this powerful halving principle just crushes the problem of finding a number in a sorted list. And that leads to a really fascinating final question I want to leave you with. This halving trick, it works on sorted numbers, sure, but what else out there in the world can be halved to find an answer faster? What other problems, beyond just numbers in an array, have this kind of structure where you can ask a too high or too low question to just chop the search space in half and find an answer exponentially faster? Trust me, the applications are way broader than you might think.